Good afternoon. It's my pleasure to introduce Moshe Zadka from VMware, who will be speaking on Make Sure Your Programs Crash. This is a 30-minute talk.
Thank you. So yeah, I'm going to talk to you about why you should make sure your applications crash, and hopefully, after the crash, recover from the crash. That's even more awesome. So I'll start with telling you a story. So I was working for a startup that was selling appliances. The customer was seeing problems. This was a key enough customer that they basically just sent me out to figure out what the problems were. So as I'm logging into the machine to figure out what's the problem, other unrelated problems, like half of the components were basically restarting every few minutes. The nice thing is these were other problems, meaning these were not the problems the customer complained about, right? Even though things were crashing all the time. And kind of the reason I'm giving this talk is to show you how you can do something that's just as awesome. So basically stuff can restart all the time and stuff can crash and nobody will see it. And that's good enough for me. So kind of the common thought is that Python doesn't crash, right? You have memory management, so you don't accidentally double free or all kind of stepping on freed memories. You don't have direct pointer arithmetic. So a lot of the common cases of crashes supposedly are like magically gone from Python. Well, that's kind of like a nice, fairy tale to tell your kids, before you put them to sleep in bed, but, it's kind of a lie. Everything crashes and burns, right? The C core has bugs. The C modules have bugs. It's kind of fun if you ever want to actually go on the Python bug tracker and see how many potentially crashing bugs are in your interpreter. You will sleep less soundly at night, but possibly no more. Exception can go untrapped. It's not always a good idea to trap all the exception because, out of memory is also an exception. Not a good idea to trap it. Your code can have infinite loops. Mine does. Right? So that's not technically a crash, but your process hangs. Who cares? You can do a blocking call without noticing it because your socket was not in the non-blocking mode that you thought it was. And even though selected said that it could be read from, it could not. That's a lot of fun. Threads can deadlock. And all it takes is one simple trying to lock two things. And you're not, of course, aware that you're locking two things because the locks are hidden far deep in some function. And bam. And the best part that happens, especially when you do trap exceptions, is you get basically to an inconsistent resident state. What I mean, you trapped an exception, you thought you handled it, but you didn't handle it properly, which means now your problem is in this inconsistent state. That's the most part, because your program looks like it's running, right? It looks fine, except it spews out errors all the time. That's even worse than a crash because you don't see it. Yes, and my point is, these things happen. These things, happen to my program, and possibly even though you're all better programmers than I am, I'm sure, these things might happen to your programs. So the important thing is you have to recover from the crashes, right? So this is a quote from an old IBM manual. If you actually read later the talk notes, they have full references. This is not a quote I made up. So basically, the idea is that you always have a recovery routine. So whenever something fails, no matter how badly, you attempt to automatically restart it. And if you do it right, then any bug the user sees is two bugs. The bug that caused the original crash and the failure to recover from that crash. So when you treat it like we actually treat it that way in our bug system. When we got a crash bug from a customer, that bug actually turned into two bugs. The real bug that we try to analyze and obviously prevent the crash, and the bug that, why did the customer see that crash? There were a lot of bugs that came onto our bug system just because we downloaded the logs and saw that there was a crash that was recovered from silently, and the customer never knew better. So the biggest problem when you crash is that whatever non-resident state, meaning whatever storage you have, will be from an arbitrary state, right? That's especially fun because you can't assume any kind of reasonable, get to a consistent state process has been done, right? The killer in Linux is a lot of fun because the killer can just, shoot your process in the head. That's it. It can easily get to that state. So you always want to assume that if your program crashed, the storage can be in undetermined state. That means that if you're not very careful about writing out data, you're like writing to two places and you're not sure what happens first, you might be actually in a place where you can't recover. Is this the right one or is this the right one? I have no idea, right? What if there's like, two counters and they have to maintain some sort of consistency, but a non-trivial consistency, which is right? I know that they're inconsistent, but possibly one of them should be right. So the idea is that you always want to maintain your storage, maybe not in a consistent state, but in a state where consistency could be recovered from. There's a very important difference, and maybe I'll get to show you examples. I'm not sure. That kind of depends on how long I will run. So the easiest way to avoid inconsistent storage is to avoid storage altogether, which you can do a lot of the time. That's awesome, right? If you're just something that analyzes resident states, and just if you crash and start up, just start up. It will be fine. If you need some data to perform better, just keep it in a cache. Caches are easy because at worst you can do the stupidest thing, which is mark cache inconsistent. Do updates to cache, mark cache consistent. If you actually make sure that by the time every operation returns to you, it has actually done, which is non-trivial. If you do it on the file system, you have to use the super f-slash method that's different between operating systems. But if you actually manage to get all this done, then it's fine. If you see that cache marked inconsistent, you just dump the cache, right? So it could be that somehow you did manage to finish it and didn't get to write that the cache is consistent, but that's fine. So in some cases, you work a little bit harder. But that's kind of the ideal to avoid storage. Unfortunately, in real life, apparently people want programs to actually have a lasting effect on the universe. So then the easiest solution that people usually go to is transactional databases, and they're a pretty good solution, right? There's a reason everybody goes to that solution. That's a very good solution. Databases have 30, 40 years by now, years of experience to actually make sure that their state is somehow recoverable, right? That's kind of where they make money off. That's why they have multiple databases caching each other and all kind of crazy stuff like that. So if you use transactions, that will just work and will sort of magically maintain consistency. That's the awesome part about databases. If you're not using one of those $500,000 databases, or however much they cost. I never bought one, but companies buy them. I have no idea how much they cost, a lot. So the databases can crash, and quite possibly your MySQL or Postgres has never been through that kind of rigorous testing, right? You have no reason to assume that someone actually made sure that every tiny bit of Postgres has been gone through. So maybe it can get into an inconsistent state if your file system is set up in a weird way or stuff like that. So you want to make sure that you kind of account for their not being able to recover from their cache. There are ways around it. If you maintain multiple copies and failover, you can do that. You just want to make sure that if you have a crash recovery algorithm that depends on the database being in consistent state, you have a plan for what to do if the database is not in an inconsistent state, even if that plan is just calling the database vendor to whom you paid $500,000 and complain. That's a valid plan. But you want to make sure that you have some plan. So if you don't want to use all kinds of funky database stuff, you can easily sort of roll your own. And basically, the trick of all your roll your own schemes that I will show is sort of one, but there's gazillions of those, depending on exactly what you need to maintain. And I've written a few gazillions of those, I think, by now. They all count on the fact that the operating system, modern operating systems are pretty good at crash recovery. If you use Linux with ext3, or I guess Windows NT with whatever NT things they have, they can actually maintain a reasonable enough state on the disk that no matter how hard your machine has crashed, if you start back up, your file system is in a reasonable state. And so the big atomic operation that you can layer whole algorithms on top of is file rename. If you do a file rename, either the rename has not been done, or it has been done. There's no intermediate state of the directory of the file rename half done, right? That's opposed to file copies and all kind of other operations. Those are not atomic. But file renames are atomic. And especially on Unix-based systems, but even on Windows-based systems, you can do like really awesome things. So the example, the first code example I'm going to show you is how to do a counter with that version. And I'll note that this example doesn't work on Windows. If you get later the talk notes in the bonus slides, which I might be able to get to, I show how to do it on Windows. But this is like the simplest code that shows you how to do atomic operations, right? So you notice that I increment the counter in memory until it's fine. Until I actually like finish writing the TMP file, also everything is fine. And then the last step is basically rename. So either the rename has been completed, and therefore I have counter.txt with like 5 instead of 4, or the rename has not been completed at the time of the crash. You'll notice that if I don't like export out the counter or make too many like tough promises on the counter, I don't really have to commit. I don't really have to do any kind of flash or magical things like that, right? Worst case, on the disk, the counter is still 4 instead of 5 when I crash, even though I thought it was 5. If I do commit outside, if I tell people, this counter will only increment even if I crash and restart, then I need to do like more things here. But this is kind of a simple code to show how you just can roll your own completely recoverable operation. You'll notice that if I crash, there might be like a spurious temp file, but that's fine. The next time I increment the counter, this temp file will be gone. So unless you really, really are like, care about cleanliness at program startup, you don't need to write any recovery code, which is the fun part about doing it this way. So sometimes this method of like maintaining the code in kind of an always consistent way doesn't allow you to also maintain it in an efficient way. For example, if you use something like, I don't know, MySQL, then I don't trust MySQL. Maybe it's just like sort of the bad rap it got. I don't trust MySQL that if it crashes, I can always recover my data from it. But it's certainly very fast, right? That's like what they all say. It's really fast, right? So maybe I do enjoy the speed of MySQL, but I don't mind enjoy the chance of losing all my data in a bad crash. So I can always mix and match, right? I can always have an efficient cache, like MySQL, treat it as a cache with like the algorithms from before, mark cache inconsistent, mark cache consistent, and then have a reliable master. Right, on top of this file rename, I can build like an interesting key value store. Again, if you see the bonus slide or if you see my talk notes, I have like a complete implementation of the key value store. So basically, I maintain a key value store and I maintain my stuff in MySQL in parallel. If at start time I notice that the cache is inefficient, I rebuild it. Of course, it's slow. Then you have a bunch of tricks, like I want to be partially available while I restart and stuff like that. I'm not going to get into all of these details right now. But that's kind of a good kind of thought model for the case where you actually want like really fast selects or really fast querying ability, and the thing that gives you the really fast querying ability just doesn't give you the reliability that you feel you're comfortable with to like commit that you'll never lose the data. So the other thing I recommend is that once you do all of that, once you make sure that at any point in your code, if there's an killer in Linux and it shot your program in the head, or if there was a power outage and there was no ordinary shutdown, then your program can still maintain. Don't write any code. Like usually all kinds of frameworks have like place to write code for the shutdown part, right? In Twisted, it's like after shutdown. In just core Python, it's sys.@exit, stuff like that. Don't put code there. Or if you really need to put codes there, put like sort of unimportant codes there, like log, statistics. If you have to do without the statistics, you'll do without the statistics. But don't put any kind of like, nice shutdown, make sure my data is consistent. Your data should always be consistent enough. And if you do that, that means that you basically crash in testing, right? Every time that QA shuts down your program in the nice, orderly way, they basically crash it because you do not have shutdown code, which means that any kind of unfortunate assumption you made that like, this will be consistent will actually be caught. Of course, then you want to train QA to like shut down your program at the most unfortunate moments so you will catch all these exceptions, right? This is, and make sure that, you have a reasonable, unit testing system that crashes the code, at least, via all kind of like mock tricks, at like the most horrible parts to make sure that you can always recover. I'm going a little bit faster than I thought. I'm very happy. Okay, so the next part is, let's assume that you've done all that. Let's assume that you've sort of been, good little boys and girls and made sure that your data is somehow always recoverable. This means that if there is a problem, you can just restart. Which means from this point on, it's not a matter of whether you can recover. It's a matter of like, number of nines, if you will. Right? If you think of it in terms of if you have a certain amount of crashes per day, then I think 5 minus the log 10 of the seconds it takes you to wake up times the amount of crashes is basically the amount of nines you have. Did I lose anyone with the math? Do it in your own heads. Anyway, but this is really the point, right? The faster you are, obviously, like, it's better if your code crashes rarely, right? This is kind of, ideally, you try to, like, write code that, won't crash all the time. But given that you had a crash, you want to restart as fast as possible. This is what gets you to, like, the high nines. What gets you to the high nines is not necessarily recover, like never crashing. What gets you is really, really fast recovery. So you want to make sure that you recover fast. So there are two ways you can sort of improve your availability, improve like the number of nines, which is you can limit the impact of any single crash, right? So maybe if a crash happens, you do not go to 0% availability, you go to 80% availability. Again, that kind of helps you on the nines. You want to detect it fast. You want to detect the crash as soon as it happened. And there are like, obviously trade-offs here. You don't want to detect a non-crash, which is sometimes tricky. And you want to improve your startup time. And basically, the idea is try to do things on all three fronts. So to limit impact, basically you want to split it into multiple processes, right? If you assume that sort of the basic unit of restartability is a process, which you do want to assume because you should never shut down threads, because that leads your program in even worse consistent state will probably lead to a restart later, just do the process restart now. Then you basically want to make sure that, you have sort of redundancy in the processes. And there are two ways to achieve that. You can achieve it via vertical splitting. The example you should probably all have in your head right now is Apache. Right? Apache runs multiple children. If one dies, it actually has kind of zero impact on availability. It just means that the other ones will have to take care of more than their share of work, and eventually Apache will spin up another, and like everything will be hunky-dory. So that's kind of vertical splitting. It works well for the kind that vertical splitting is good at, which is, luckily the kind of thing that web servers are good at, which is why Apache does it a lot, right? Which is like you don't need to communicate a lot between different execution streams, right? If you have a single HTTP request, it's perfectly reasonable to assume that it will not have to touch any other HTTP requests while being served, right? If you have sort of shared data, you have kind of a backend, MySQL or and message queue or whatever it is you have. But as they're served, they probably shouldn't communicate too much. So that works well for the case where vertical splitting makes sense. The other kind of style that usually is in tandem with vertical splitting, but sometimes is used purely on its own, so for more interdependent servers, is horizontal splitting, right? So if the vertical splitting is kind of like an army, everybody is exactly the same, right? Like you have like 100 soldiers marching in line. A horizontal splitting is a surgical team, and much like the difference between a surgical team and an army, the surgical team is much smaller, right? If you do horizontal splitting, usually you get 10, 15, 20 processes, right? In vertical splitting, you very often, get into the hundreds of processes, right? So that also impacts availability. In horizontal splitting, you usually have less of a good impact on the availability. On the other hand, in horizontal splitting, quite often you sort of localize the problems. Usually there is a particular part of the program that's more sensitive, that tends to crash more. ideally that part will just sort of crash on its own without bringing the whole system down. And if you sort of set up the other processes to never completely trust it's out and kind of say to the user, I'm working on it, wait a minute, while kind of waiting for it to restart, then often this gives you a pretty good approximation of availability. The last part that's more necessary in the case of a horizontal split than a vertical split. Right, in a vertical split, one of the processes died, so what? 1 out of 100 died, the rest have 100 over 99 times the work, nobody even notices. In a horizontal split, if one of the members of your surgical team is missing, you want to know that really fast and replace him with someone that's working better. So basically, that's the job of a good watchdog. And kind of watchdog is an overloaded term, but unfortunately it is sort of the term I usually use for that, so I just prefer to sort of go with terminology I'm used to, but it will come back to bite us in the ass later in the talk. So the watchdog basically is supposed to monitor, look for problems, flag the problems, and remediate the problems. And usually the remediation is kill the process, start up another one instead. So the watchdog should not crash, right? I hope this is kind of obvious, right? If the watchdog crashes, then nobody watches it. And then it's sad. We actually had this problem not because of a watchdog crash, but the killer kills the watchdog. And then things started, it was bad. Later I will talk about how to sort of compensate for that. But in any case, usually the common compensations for that are doing very, very big things. So even if you did have this in compensation, you still want to make sure that the watchdog doesn't crash unless something is really gone out of whack. So the simpler the watchdog is, the simpler, obviously, the better chances you have to not have it crash. So basically, if you want the watchdog to be simple, you don't want to start it communicating via sockets or stuff like that, because that will complicate your watchdog. Then your watchdog gets stuck on a blocking call, and again, the whole system sort of falls down to its knees. So what I have here is the example of the way I like to do heartbeats, which is basically touching a file. The nice thing about touching a file, you can check it offline, right? The watchdog doesn't have to be sort of closely aligned, right? If the watchdog comes half a second later, you can see that the file has been touched. Right? So basically, the way I usually like to do it is to sort of beat. So this is a simple beat from how you would do it in Twisted. You sort of put this code somewhere in the beginning. And if you actually do that, then this means that as long as Twisted's event loop is running OK, which means nothing has blocked, nothing has crashed, nothing has gone in a thread deadlock or something horrible like that, you'll touch the file. As soon as one of these happen, as soon as you get into a thread deadlock, or as soon as you try to just stupidly import URL lib and urllib.url open from inside your Twisted against a web server, in case you're wondering, this is not necessarily your fault, right? You might be calling another library, for example, an XML RPC library, which helpfully tries to retrieve the DTD. Right, that's a lot of fun when you do that, yes. And basically then your Twisted process gets stuck, right? And it's completely not your fault. This happens. So if this happens, it won't touch the file for 30 seconds, and later we can see how the watchdog can monitor that. But you can have multiple beats in the same process. So if your Twisted program also launches a thread that has to do something every hour, then you make sure that in that hourly cycle, you touch a file, and then you set this file's sort of bit rate to an hour. We'll come to that in a second, I guess. So again, I don't want to put complicated parsing complicated parsing logic in the watchdog, because complicated parsing logic again, makes the program more complicated and more likely to fail. So basically, I use a file system as kind of my parse tree. So I just put a lot of hearts, and each heart says, the file is the heart name, and the content is just an integer, right? In real life, I would have a try except around it, but later on I will explain why it's not necessarily important to have the try except around it, but I want this to be simpler. So basically, parse all the hearts, and then I know how long each bit has to go before it's pronounced dead. Okay, so that's kind of really simple. In our code, I actually sort of called it the EKG, and I used lots of medical metaphors. The patient died was a log message. It was very funny. Less funny when customers saw it. So basically, sort of the way I kind of envision a watchdog, and I sort of regret to say I did not do it the first time I implemented it. I learned from experience. Maybe that's good. The watchdog just marks problem. It doesn't actually try to do too much about them. So in this case, it basically just, whenever it sees a problem with something, it just tries to be a little bit careful so that the M time of the problem file will be when the problem was first noticed, and not when the problem was last noticed, which is a fairly useless number. But other than that, basically just puts the problems there for something to do. Right? A lot of people have like the watchdog and the process like sort of starter in the same process. That's bad because the watchdog should be simple. Right? Again, we kind of had a lot of that, so that's learning from experience. Oh, you'll notice that I put this as the content. Sorry, there was one other thing I wanted to say before that, where that I put in the content the watchdog. That's obviously not necessary for anything, but it will come in later. Like ideally, if something does actually remediate the problems, it will say problem detected by watchdog. So you can actually have multiple detectors, and they can mark it down, and ideally it will all be nice log files that you can later analyze to figure out what went wrong. Haha, success. Okay, so basically the watchdog, all it does is it checks that someone solved it. Right? It doesn't actually try to solve the problem. But if a problem, a single problem has gone unsolved, what the watchdog assumes is that the guy responsible for fixing problems is gone. Now, the watchdog is not going to have complicated problem-fixing logic, because again, if you have complicated problem-fixing logic, you complicate the watchdog. So ideally, your thing that monitors the problems doesn't crash a lot. If it does crash, the watchdog has sort of the one solution, which I call the nuke them till they glow and shoot them in the dark. And the reason I call it is because kind of like a lot of this kind of amusement is hidden inside the restart system, which I will not show you, but I will sort of tell you a little bit about what's going on there. So ideally, what happens in the start system is first the watchdog goes and finds like the log of the thingy that. So again, the nice thing about it is this is an external script to Watchdog. So if this script has issues, then this is not Watchdog's problem. Right? If this script hangs, ideally it shouldn't hang, but kind of Watchdog will come in and try to rerun the script. So if it was just a temporary problem, then this script will run again. But this script goes into the whatever thing started the processes, looks at the process IDs, and then kills them, and then basically the shoot them in the dark is basically, if you do it correctly, the process monitor sort of stamps itself, and by extension its children, with kind of a marker, which is an environment variable. So it sets an environment variable like my descendants to like some long UUID. Then the watchdog, especially on a Linux system, can go over the process list, see who's marked with that mark of the UID, and it knows it has to kill them all because they were part of that whole system that needed to be restarted. So it basically really does nuke them till they glow and then shoot them in the dark. It tries to eliminate anyone who was part of that whole conglomerate which failed, and ideally then we start the system from scratch. So with that kind of separation of concerns, so you do the common solution to problems in a reasonable way of something that can sort of, just pick the given process that had a problem, try to send it a 15. If it doesn't respond, send it a 9, check it died, all that kind of sort of niceness. And then basically when the watchdog sees that the problem has not been solved in enough time, it basically completely destroys the whole system and makes a new one. And the loop is fairly simple. Ideally, the marking of problems and checking of solutions, in the case where there are no problems, is just reading a directory. Again, kind of most of my experience on the Unix system, on a common Unix system. The way it works, okay, I'm almost out of time, so I'll kind of skip over the next few slides. Wow, I thought I was. So my conclusion is everything crashes. You should plan for it, because if you don't plan for it, it will still crash, but you won't have a plan. So that's it, and I am happy to hear any questions you have.
We have time for a few questions. If you could please come to the microphone over here if you have a question so that we can all hear you. So I guess I have a quick question. So it seems like you were presenting the Watchdog in small chunks, which all in and of themselves seem fairly simple, but taken as a whole seems still relatively complex. Have you run into issues with your Watchdog, and how do you resolve those?
That's a good question. That's kind of the two slides I kind of skipped to get to the end. What I presented, the loop, is just a Python process. If you want to get like better reliability, because these are just two parts which have nothing to do with each other, you can run each of them from cron on a 1 second basis. So basically, like, you sort of depend on the reliability of cron. Then you get into the issue, okay, what if cron dies? So basically what you do is, from these things, after you do the interesting thing, you also touch a file. And so you have these two files that have to be touched all the time. Then you can use the Linux Watchdog. That's kind of the kind of horribleness of the Watchdog, that, you know, there's like lots of things that uses that name. So use the Linux Watchdog daemon to monitor these two files. And when the Linux Watchdog daemon, what it does is it opens the Linux hardware or sort of software emulated in kernel Watchdog device, and it has to write to it all the time. It won't write if it either crashes or if one of these two files is missing. If the Watchdog doesn't write to this file, then basically Linux reboots. So basically, this is kind of yes, you have to be sort of insane and paranoid and make sure that, yeah, so that's a good question. Yeah, so I was going to sort of go over that. So yes, if you're insane and paranoid enough, then you get into the situation where, as long as Linux has not gotten into like a really bad state, which is unfortunately impossible to prevent from user space, then eventually your process will restart. Thank you, Dan. What? And you can use a hardware watchdog if you're really concerned about that, and Linux supports it just fine.
So the sysadmin in me actually is horrified by all of this. I think this makes a lot of sense from a developer's perspective, but you know, if I have a cluster of 100 machines running your software, and you know, disk goes bad, RAM goes bad, I mean, hardware breaks, and if the response of your software is to try repeatedly to restart itself every second, spamming messages, spamming brokenness, actually don't want that. I want that system to just go away.
Excellent question, Dustin. So yes, I kind of started the whole story by talking about the appliance that we were writing. So an appliance doesn't have a sysadmin. An appliance is supposed to just work. Ideally, you should, you know, you should be able to just run it without the watchdog. Kind of the nice thing about this watchdog is it sort of it just marks problem. You know, if you sort of tweak it a little bit, you can mark it as problem without checking for solutions, and then like you can use a system without restarting, and it will just sort of, you know, you can like, you know, sort of output it to like make sure that it sends you an email if there's any problem file. Yes, this is for systems that do not have a sysadmin, because a sysadmin would indeed be horrified by that. This is for systems that just have to work without any user intervention, including sysadmin, which is still a user. Thank you, Dustin. I think I'm out of time. Yeah. Thank you.